All right, hello. Hello, world. Um, so last time I had been talking about, we did 3940, I believe, but I was a little confused on some comment in 39. It turned out to be pretty straightforward. Um, Two issues. So 39, just a quick recap. We were showing this, and obviously I would have been stumped until I looked at the answer on 39, but it's actually pretty straightforward. Um, I was like, how do I get just that one term on the bottom? How do I just get the odd ones? Well, I mean, you don't. What you do is you use binomial theorem expanded to the power n plus k plus 1, and then you take the 2k plus first coefficient of that. That's about it. Then you do some fiddling. And then there's a trick where he multiplies by x squared to the n plus k, or probably n minus k, I should say. And it cancels the x values and allows you to it allows you to say that it's the coefficient of 2n plus 1 instead of 2k plus 1, because otherwise I would have been very confused because the sum is over k's. So he's got this extra term there that really saves the day, this extra factor. But anyway, so after I sorted that out, I was confused at the end because this equals this. I got that. But then he immediately says, or the power series of this, which is not the same function. And then he follows up with division leads to a polynomial degree n2n, sure. And the remainder is blah. And I was like, how is he computing this remainder? But the rest of it makes sense. Anyway, he didn't mention it because uh, you could think of it as a basic fact of polynomials, or you could use Taylor series expansions. You could use Taylor remainder's theorem basically to say when you divide by 1 plus x squared, the leading terms are going to look like the function at the value. So, well, I'll talk about it in a sec. But and then the other thing is he's ignoring this chunk and just looking at the front matter because this numerator is lesser degree, or I should say greater degree, excuse me. Yeah, what he factored this part out, and the stuff that's left in the numerator is too large of a degree to affect this. So that's why it was irrelevant. So he's looking at just a simpler power series. So I was wondering where the remainder comes from, and I was wondering why he was able to just ignore a factor as part of the answer, But we're going to see if I can sort of explain that. For one thing, we're looking for degree 2n plus 1, the coefficient of that in this expansion, right? So if you factor this out, the 1 plus 2x to the n plus 1, you get this, right? And we're going to include the denominator in there, and factor that out as well. And the stuff that's left would be 1 minus you can see it's negative x squared to the n plus 1 initially, right? And what he's factoring is 1 plus 2x to the n plus 1. Oops. He's factoring that out of both, right? Both terms in the numerator. So it looks like this is what he left. But if you anyway, if you look at the degree of this thing, you've got something on top that's like 2n plus 2, right? I realize we have 1 minus this stuff. So that on its own, that would not have affected the 2n plus first coefficient. Like if we multiply by that, say we have some stuff here, and we want to know like the second coefficient. If you multiply by something like that's larger degree, there's no way for it to contribute, right? Obviously. So what I'm saying is this stuff that was left over is of degree 2n plus 2. And part of the reason is there's a constant here. I know you might, like my instinct initially was like, well, doesn't it cancel? But this is just a geometric series, okay? It's just like, it's like if we took negative x squared times negative 2x, well, I guess I forgot the 1, right? This alone is already of degree n plus 1. So we've got this plus this squared, da 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 da, right? And we're going to take both of these things and raise them to the power n plus 1. So you're going to get 2n plus 2, and you know, even if you multiplied it by 1, the smallest degree thing there, it can't possibly contribute to a coefficient that's less than this degree. So if this 1 was not there, then we'd have troubles. If this was some if this was 0, then it does bring the degree down by dividing by it. You see what I mean? But the way it's expressed, even if it was like a 5, we could divide and we get some geometric thing, and that begins with a 1, and so you never get anything smaller than x squared inside this, is what I'm saying. So that explains why you're able to just factor this and group the 1 plus 2x, and that explains why you can just drop the remaining factor that was sitting there and just consider this power series. Okay, that's part of it. Division, meaning if you actually did this division out, we were looking at something like half 1 plus 2x to the 2n plus 2. And we were talking about dividing it by 1 plus x squared. And he claims the remainder is this. So the division would of course be a polynomial. It gives you some polynomial of degree 2n. That makes sense. But then I was like, how would you possibly get this remainder? So again, we'll see if I can make some sense of that. Let's say our polynomial upstairs here, we'll call it f, but this is some polynomial. And here's our divisor. Let's see. If you had a polynomial and you divided by x minus r, right? You'd get some constant term, and then you'd have a did I say that backwards? You wouldn't have a constant term. The numerator, like the result that you would get, the quotient, I should say, not the numerator. The quotient, it would be a new polynomial that's 1 degree less, right? If you do your long division out, you get a new polynomial 1 degree less, but you also probably get a remainder. And because this is linear, this numerator have to be a constant, right? So one quick observation is if you divide by something squared, the remainder term is a line, right? It's going to be that divided by your x minus whatever squared. And the other thing to observe, this is sort of true for anything you can write a Taylor's expansion for, a Taylor series for, but it's sort of especially true for our polynomial guy. You can think of f as sort of the function valued at r plus the derivative at r times this. So you could take, I'm saying you could in general take a Taylor's series expansion around this number r if this is what you're trying to divide by. And what'll happen is you'll get this expansion. When you divide by this term, you get what's a good way to say this? We get some stuff that's of this order, right? The rest of the stuff is that or bigger. Yeah, it's not a terrible way to say it, I guess. Anyway, we get other terms here like higher order derivatives times higher powers of x minus r. And so when you divide this function by x minus r squared, this is the remainder, right? And this is the polynomial part, which has positive factors of x minus r, and one out front that's like a constant, potentially, right? So this is your remainder term, is what I'm saying. Well, whatever. That's fine. And that's almost the whole explanation. So this is our function, and our r value is, we have x plus 1. So our r value is -1. So just compute your polynomial at -1 and take its derivative and also evaluate it at -1 and then multiply by this and see what you get. So our polynomial right, it also has derivative let's see, the chain rule, the 2's would cancel, and you pull this down. So I'm getting something like 2n plus 2 times the original function to the 2n plus 1. So that's the derivative. And then if you plug in -1, here you looks like you're getting, well, this is an even power. So we do get -1, but it's squared. So you're getting half. And then the derivative at -1, this time it doesn't cancel. That's an odd power. So you get negative of this number. I'll just factor, I guess, for a moment. I don't know if that's going to help. But yeah, you're getting this remainder where this is x plus 1. So the remainder term should be like half plus negative 2n plus 2 times x minus r. And he had an extra, for some reason he factored the half out of this. So he's getting half 1 minus, he just includes another 2 for some reason. 2n plus 2 to x plus 2. That's what you would get as a remainder, right? This over x plus 1 squared is the remainder term. Why is that relevant? Because when you divide by this, you get a polynomial that's lesser degree than we care about. We're trying to find the coefficients for 2n plus 1. So when you divide this out, you do get a quotient that's of degree 2n. Then you get a remainder term that looks like this. That's what we just jotted down. And so that's the thing that you want to find. Like that's this. If you divide this by 1 plus x squared. So that's the series that you want to find the coefficient x to the 2n plus 1 in. And I talked about that last time. We did that last time. So I will move on now, but that's a rough sketch of what's going on at the end here. Like, how did he get to this power series and how did he get that remainder? And then we had done 40 last time. 41, I haven't looked at the answer yet, but I probably should. Well, I'll take a look. I'll try it first. So 41, excuse me, says, take these two functions, phi and psi, and then show that this happens. I wonder if there's a good way I can like actually, I have a better idea. Let's do this. All right. Where are we here? Yeah, give me a moment. There we go. I could, let's see. Did that work? Nope. That's strange. I don't know why it didn't work. Alright, we'll try again. Did it work? Nope. Okay. Whatever. Actually, I can just fix it in OBS. So I'm gonna give you an image of I figured I'd tack it on in the corner here so you can see what the heck I'm doing. Of course, the problem is it's upside down, right? Wait, I figured I could like rotate this. I can't rotate it in OBS. I must be able to. There it is. There it is. I think that's probably legible. Let me take a look. That's pretty good. That's pretty good. There is a second part to this that I haven't looked at. So I'm looking at 41 here, as you can see. But there is a second part. So he did this with a sum, and he gets 2 to the n psi. And then he does an alternating sum. He gets alternating n factorial. Oops, sorry. Alternating n factorial. So I'm going to see about that part too, I guess. We shall see. Oops. Let me see how much luck I can have. Where are we here? Well, you can't see it. Something like that. So yeah, give me just another moment. Change this to something. Let me see real quick if this is legible at all. Not really, but see what we can do. Let's move this up here and give you a new image. David's embracing technology. And again, well, we can make it a little bigger. But again, we're going to flip this upside down. How did I do that again? It must have been a transform. Whack. All right, sir. Yeah, I don't know how legible that is, but I've seen worse. All right, I'll get back to it. So I haven't really looked at this one. I don't know. And I can't read it on the screen there, but presumably you can. Actually, maybe I'll just open the file for myself. There we go. All right. So we've got these two functions. Phi is you're gonna drive me crazy. Phi is it? Is that true? All right, phi is a naught, a1, x, a2. I was thinking about this last night, but I wasn't able to like write anything down. And so on. I mean, at some point you get 0 and there's no point continuing, right? Like if you plug an integer in here like phi n, so say you plug in phi 3, you get 3 minus 1, 3 minus 2, and then finally the next term is just 0 and it's going to remain 0. So you never see a4, a5, a6, or whatever. You never see anything above an in the definition of phi n. And then, of course, psi x is defined. I don't even really know. I didn't get a good look at it. We're dividing by powers of 2. 2 to the 1 with a single factor. This is a2, 2 squared with 2 factors. And then a3 is over 8 with 3 factors, I presume, etc. And I'm supposed to show this thing. The only thing I noticed was, like for instance, phi n. Yeah, I didn't get a chance to explore psi n, but well, here, I'll just go ahead and do one. For instance, phi like 5, you'd get a naught, you get 5 times a1. So you just get one factor from 5. You get these falling factorials, right? Descending factorials that stop. Or you could think of them as permutations. So this is 5 permute 1. And then we're going to get 5 permute 2. So obviously we have nicer ways to write that. But you'll never see anything higher than a5, you know. 5, 4, 3, 2. So on a5, of course, we get 5 factorial. But after that, you're getting a 0. And so it stops there. It is a finite sum. Another way we could write these, you know, the kth term is given by, for instance, here it's 5 factorial over 5 minus k factorial. Like if you want the second term, you're going to divide by 3 factorial to cancel out, right? Just pulling up another example for me to look at in a sec. All right. Well, anyway. So I'm looking at 41. All right. So anyway, the kth term is, well, for this example, in general, right, this is, the kth term would be like n factorial over n minus k factorial, and that's the numbers that are there in front of. So if you looked at like phi, I don't know what you want to look at. Let's call it phi k. Or let's call it phi I, right? You get a naught, a1 I, etc. Um, the kth term is given by a sub k, and it's I factorial over I minus k factorial, right? Pretty simple. So then I noticed that there's like a little bit of interplay between when you look at this. Can you see my? No. Well, anyway, when you look at this right here, and choose 0, phi 0, and choose 1, phi 1, etc., up to n, phi n, we are, of course, looking at, let's do, I don't know, let's call it j, right? J goes from 0 to n. We get n choose j, phi j. That's 0 to n choose j. And then the phi j we just defined as a sum of, did I write it down? Oh, I didn't. Well, it's the sum of these terms. Phi j, so like we wrote down phi I as a sum, right? I'll say it here, okay? Phi j would be the sum as you let the k terms go from 0 to j. And what you get is this, ak j factorial over j minus k factorial, right? So I did notice that we could like introduce k factorial on the top and the bottom. Or sorry, I meant, what did I mean? I was thinking we could turn this into a combination. So yeah, k factorial, but unfortunately that's inside this. But that could maybe help us. I don't know. I'm saying it's the same as k factorial j choose k ak, if that's helpful. So yeah, what I wanted to put here was phi j. That's this series. And I noticed that it's nj times jk. You know what I mean? I don't know if that's good or bad, but so let's go ahead and grab it. So I got here, just sort of pushing things around last night on my phone. Not a great way to do math, by the way, on your phone. So this is the left-hand side. I get this mess. And I thought about maybe interchanging the order, because I did notice, like, say as the j's go from 0 to n, your k's stop at j, so you're getting something like this. You're talking about this region, right? So we could maybe exchange the order. We could maybe interchange the order of integration here, but the order of summation, I should say, I guess. But I didn't bother to do it. Just I didn't really see it working out for me or like doing anything special. You could, I mean, if we take these apart, right? I saw that the j factorials cancel, but like then what, you know? You've got n minus, you've still got like, there's some harmonic series stuff happening, like partial harmonics. So I did notice that you're getting like partial sums of something that would, in the limit, become e, but that's not particularly relevant to us. Um, anyway, the right-hand side, so this is our left-hand side. Um, the right-hand side is 2 to the n psi. That I have not looked at. So 2 to the n times this. Of course, again, with phi n, it terminates at the nth term, right? So you get something like, here, I'll just leave that there. You get this. With an n there, you'll get a single n. We could write down the sum in a second. With a2, you get 4 downstairs, and you get n times n minus 1, etc. But it's finite because you plugged in an integer. So the biggest term you get is this guy with an n factorial sitting there. When you multiply by 2 to the n, all these denominators are gone. So you're getting, let's see if I can, like, you're getting, say, ak, as it goes from 0 to n, and then 2 to the n minus k, right? And then you're also dividing by powers of, oh, did I already take care of that? I did. That was the 2 to the k right there. So then you're also, you've got your n factorial over n minus k, is it? That doesn't feel right. Is it just k factorial? Let's see. For the smaller ones, you get very little, so it's got to be, yeah, it's n minus k, right? It's same thing we had before. Yeah, of course it is. So for the nth term, for instance, downstairs n minus k is 0. The previous term, you also get the sort of full, you know, sort of like analogous to this part. You also get 5 factorial for a4, or you know, you also get n factorial for the n minus first term. But yeah, other than that, I think we're in good shape. That's the right-hand side. So we're supposed to be showing that these are equal. And I get like n minus j and j minus k down here, you know? Like another way to write this, if you wanted to get rid of the if you want to get rid of the binomial coefficients, you could cancel the j factorial and the k factorial. But we still end up with n factorial on top, and it almost makes more sense to just do this, you know? So yeah, like I was saying, I didn't yet try to interchange the order here. But it's conceivable that that's helpful. I suppose we would just be letting k go from 0 to n, and then where am I up here? When you change the order, the j's then go from k to n, you know? So another thought I had on the left-hand side is that you could do this. I'm not sure it's going to make a ton of sense, but you then let j go from k to n, right? It's the same region. Of course, I didn't actually do any reindexing or substitutions, so I don't know if that's going to make any sense at all. All I did was swap it. I did the boundaries correct. I didn't bother to like check anything. So I would not be surprised if it makes no sense. But it's the same expression, so what could go wrong, right? Yeah, and choose j still makes sense. It's fine. So we're getting, you know, k factorial nj jk ak, like that. That's still our left-hand side. It's another way to think about it. Don't know if that's helpful. We also, notably, did we do anything with these? I don't recall this coming up. We did it with squares. You know, we did like the sum of the squares of various on the previous page. But we didn't do anything just directly with products, so it's not like I have a formula in my back pocket for products of these guys. You know, the j's cancel, and n factorial is part of our answer. Well, yeah. So I guess, I mean, obviously part of this is there already. So I guess if I could show, you like my scribbles? If I could just show that the sum from k to n of nj jk is equal to 2 to the n minus k nk, right? Statement makes sense? Because the rest of it's there already. We could even just factor that stuff out, and then everything matches. So I just want to know that this sum, yeah, equals that. Curious, right? So of course, I mean, I don't think me taking this apart is going to help, right? We get n factorial and then you've got an n minus j, and over here we get also mean, don't I get both terms here? I get a k factorial and I get a j minus k factorial. So that didn't really, well, it certainly doesn't give me that, but it's doing something, um, right? It gives me part of it. If I force it to be there, and then, you know, multiply and divide by this, so yeah, we've got this mess. So I've boiled it down to, is it true that this is 2 to the n minus k? Right? Wait, I didn't take a sum. No, so that's not what I meant. Sorry. I didn't take a sum. But I'm summing over the j's. So is it true that this sum from k to n is equal to 2 to the n minus k? I mean, evidently it is. That's a strange sum for me to deal with. K to n. N minus k factorial over n minus j and j minus k. Yep. Anyway, if I proved that, part A is done. So, alright. At k it cancels, and at n it cancels, and gives you just this each. It doesn't look like it's a power of 2. And this part doesn't even. It's okay though. We'll I guess, do we leave it there because some of the time it cancels? So this left hand side, some of the stuff we get is, I guess we get 2 of these. Right? Anyway, at k plus 1, hey, wait a minute. Why do we get this? This cancels, and this part is just 0, so you get 1. Yeah, 1. When k is 1, you get, sorry, k is never 1, dude. When you plug in k, I didn't plug in 0, no, I plugged in k, good, k. When you plug in k plus 1, you're getting each, just this, right? You get n minus k minus 1, so you get just this top factor over 1 factorial, right? You then get two terms of a falling factorial, but this time it's divided by, this is a k plus 2, so you get 2 factorial. I guess we can do one last one. But it is a very symmetric thing. For instance, at the end, like when you plug in n, of course you get 1 again. When you plug in n minus 1. So let's do n minus 2, I guess. Maybe not as symmetric as I thought. Doesn't that cancel? Let's see. Say you plug in n minus 2. You got no, it doesn't cancel. Got confused for a second there. Yeah, you get two factors, so it is kind of symmetric. If you plug in j equals n minus 2, right? You got n minus k minus 2, which leaves me with like two terms, this guy and that minus 1. So that's how that part cancels. And then again at j equals n minus 2, this becomes a 2 factorial. So it is symmetric. At n minus 1, same deal, this becomes a 1 factorial. This becomes canceling everything except that term, you get this guy back. And of course you get a 1 at the end. This is a I wonder if it was like easier to have left it as this. Like, nah, that's fine. I just don't know why this would be 2 to the n minus k though. Like, another way to so this is the same quantity, right? Wait a minute, am I done? Something's fishy about this. Like this I know is 2 to the n minus k. It does look suspiciously like this series that I just jotted down, doesn't it? It is this series. How come it wasn't obvious? Yeah. Okay, that's part A. wondering why it wasn't obvious to me. Oh, because there's no j factorial here. Because this is, you know, yeah, it's just different. And minus k minus j factorial. This is the same as, like, you see what I'm saying? Like, evidently, well, the indexing is different, first of all. So it's just reindexed. Yeah. Why are you flipping out about this? This is very easy. Change this. It's just a reindexing. Okay, I see. Like this, of course, is equal to this with some reindexing, right? Just change the variable. So, you know, subtract k from the j's. Why does that sound so wrong? You're doing a shift here. Like, take this series and subtract k units from the j values. So if I did a substitution like I is shouldn't it just be j minus k? Like, shouldn't it be that simple? And then, yep, that's it. So, did we change upstairs too? We must have. No, because it doesn't involve j. Great. So, by this substitution on this series, you're going to get, of course, j is I plus k. How did I manage to botch this? This part's the same. I goes from 0 to n minus k. There's no problem there. Yeah, I don't know what you're flipping out about, man. And then j is I plus k, so we're getting n minus, I'll just write it here, n minus, see what I'm saying? N minus k minus I. And then this is I. So here I goes from 0 to n minus k, which is how you get n minus k, choose I, which, by the way, is, of course, 2 to the n minus k. So, alright, good. So by the substitution in this thing, we're getting 2 to the n minus k. So that was really pushing some definitions around. That wasn't so bad. The second part, let me just like use a whole new paper for that. 41 part B, I guess. We've got left hand side looks like this. And choose n phi n, and it's supposed to be equal to, this time, an alternating thing with an and n factorial. So, I wonder if there's a way I can kind of, no, I don't see it. I was hoping I could like somehow cheat and use the first result, but I guess it's not gonna happen for me. But again, we do know the fees, the phi, you know, is a formula that I had for phi j, phi I, whatever you want to call it. In general, phi is a sum as k goes from, say, 0 to j, factorial jk ak, like that, okay? And this time we're not using the psi at all. So when you sum, say as j goes from 0 to n on the left-hand side here, and choose j, well, there's an alternating bit I'll throw in here, but here's, well, whatever, I'll just do it now. -1 to the j, phi j, right? Yeah, sure. Looks good. That's the left-hand side. So our left-hand side is also this. So again, you've got this, if you want, k goes from 0 to j. So you could interchange the order if you want. It's a finite sum, so it's definitely, it's convergent. So if you want, we can sort of immediately, instead of going from 0 to j, we can go from j to n of wait, what? What? What are you saying? We can go from 0 to k and let j go from k to n. And then here's j, still dependent on j, and this chunk is our phi j, k factorial jk ak, like that. Now I want this whole sum. But part of it, yeah, I don't know. Am I able to get a formula for this part? I kind of doubt it, right? Well, apparently something happens, so. Unfortunately, the right-hand side is not anything fancy. Well, this looks symmetric again. Right? As it goes up, this side goes down, etc. Look at this alternating business. But how is it going to actually just end up being the one term? it's acting like everything cancels except for that last term, right? So when k is n, you just get when k is n, you just get 1. You get negative 1 to the n. I guess the whole thing you get is that one term. Right? So it does equal the one term we're after. Obviously my task is to show that this is 0. Not this, but the whole thing. It's a little wacky. This k can be involved, but clearly the AKs can't, right? Somehow, with these weights, it still cancels? I don't think we know anything about the AKs except for the previous problem. You know, that 2 to the n psi of n result. I mean, yeah, if we showed that this was 0, obviously that would be very helpful. Clearly that's what's happening. It could still involve k factorial, I guess, but I don't see how that's going to help anything. This alternating junk is 0. Can you show that that happens no matter what k is? Really? So suppose k was n minus 1. You get 2 terms, so you're taking a difference of them. You get 0, actually, right? Obviously. And choose n minus 1, n minus 1, choose n minus 1. You get n. You don't get, hold on. Oh, yeah, you skipped the other term. Huh. It's very strange to me. Alright. We'll give it a shot. For the case of k being n minus 1, this stuff is, you know, then j is n, but k is still n minus 1. So yeah, it gives you 0, of course. For another number, like just generally k, well, no, because we need to sum up as it changes. So yeah, what do you get in general? I guess you get negative 1 to the k, and k, k, k. plus 1, and k plus 1, k plus 1, k, and so on. It's not going to be an induction, is it? Like, it's clear for this case. Could I then, like, extend it to n minus 2 and then just say we're done? There's more terms here, obviously. They stop at n. But we could stop at the n minus first if you want. Let's say j was n minus 1. Right? When j is n minus 1, you get this, and you get this. And the last term is negative 1 to the n. Something like that. So there could maybe be another reindexing trick, right, that I'm not seeing. If we just do the same exact reindexing, this time we have a negative 1 to the j in front of it. I forgot my k factorial, but it does cancel if you want it to. Wait a minute. This seems familiar. So we were going from k, like this sum, whatever, I'll just write it again. This is the sum from k to n. And if we look at the sum instead from like 0 to n minus k, you know, we do the substitution. Then you're looking at alternating j is I plus k, and you're looking at n minus I minus k times I factorial Did I mess that up somehow? Not really, no. So these match up, although you don't need... Was I able to get rid of the n? And now... Okay, well... Because this is, of course... this isn't really the point. I plus k... Is it minus 1? Plus 1? I can never remember. I think I want minus 1 here, right? Anyway, times an alternating negative I. Negative 1 to the I plus k. This is actually n minus k, choose I. So we've got some constant times and alternating. Yeah, this is probably like a basic fact that we would have shown. Do you have this equals 0 anywhere? Son of a... No. No. But we did have this. Wait a minute. Yeah, did we never showed this equals 0? No, we did it with powers. We had this guy. Like, this is true, but there's a power in the way. I don't actually have that. It doesn't mean this is wrong. Yeah, why are you even thinking about this? Of course it's true. This is 0 because it's 1 minus 1 to the n minus k. Yay. So that's 41. So it was the same trick. There's another re-indexing. Not bad. What does he say? I'm sure he crushes this in like one sentence. 41. Huh. Yeah, I did do it a little differently. Just a little more organized, I guess. So, yeah, these are kind of obvious statements. I didn't write them down like that, but I used those. I mean, I used it as part of the summation, these facts. So then you're looking at this thing. I don't see him doing any re-indexing trick. Yeah, how did he get there? It's this times 2 to the n minus p. Okay, there's the re-indexing trick. He didn't explain that, but that's why that's 2 to the n minus p. Because it's just binomial theorem. This part's fine. I just didn't follow his first. And then for the second one, same thing, right? He's going to be 0 if... Yeah. So he didn't comment on it, but obviously that's another binomial theorem. That's why that's equal to 0. So the only issue I have is like, how'd you get from here to there? I know you could factor the n out, and you've got v minus p and p factorial. Okay, so there's that, and then the other one is n. But why would it be p? I don't quite follow this. See the v... Oh. Right. He changed it. Huh. Let's see something. He said something like, he's looking at NV, VP, right? V equals P to N. So if I didn't go any further, we've got an N, a V, N minus V, V, P, V minus P, right? He pulls the N and the P out, of course. And then we're still left with, oh, the V's cancel, that's fine. So we're still left with this. He doesn't reindex yet. What he says is, he gets an N minus P here, which means he clearly multiplied by it, right? Put it in the numerator. So he like put N minus P here. And yeah, then you could reindex. He doesn't. I guess you don't have to, huh? He actually leaves it. Does he leave it as P to N? And then he just says that it's, yeah, he does. He leaves it as P to N. P to N, and he points out that this is the same as N minus P, N minus V. Of course, if you subtract N minus V from this, you'll get V minus P. So yeah, there's nothing wrong with that. Huh. Alright. That's pretty slick. That does contain the same stuff that we did, right? Like the first chunk is just figuring out what the series is, another way to write the series in terms of binomial coefficients. And then there's the reindexing trick that gets you the binomial theorem, just giving you the answers, the last step. And then here, what did I do instead of that? I mean, I guess I kind of just took them apart. So I basically just did it without using the notation of binomial coefficient. So that's 41. I think maybe I will stop there for the day, just in the interest of keeping it, you know, keeping things clean. Don't waste too much of anybody's time. 42. This infinite sum, well, I doubt it's actually infinite, but this sum, like up to n, as v goes from 0 to n, you get this. 0, number minus n squared, number minus n squared. It never changes, it's always a square. How would I get that? And then it does the same thing but with an alternating series for 43. And then 43.1, verify this identity. This equals this. This kind of looks like just an application of, you know, our previous guy. Although you don't have any binomial terms in your thing. It might cancel out though. So what I'm saying is for 43.1, you could just say you put the e to the x on the left-hand side. Well, it's the sum of x to the k over k factorial, right? So it's like a 1 in the numerator all the time. And then what he put there was an alternating over n, x to the n over n factorial. So yeah, again, looking at 43.1. You have something like here, alpha is 1 all the time, and beta is given by this formula over k, like that. The product of these series is a new one. Let's call it gamma, like gamma k over k factorial x to the k, right? Those terms will be given by alpha 0, beta n, plus n choose 1, alpha 1, beta n minus 1, plus n choose 2, alpha 2, beta n minus 2, etc. So in our case, all the alphas are 1, and the b's are just alternating, you know, negative 1 to the n minus 1 over n, n times negative 1 to the n minus 2 over n minus 2. Yep. Wait, what? N minus 1, sorry. So yeah, we're getting n over n minus 1. Huh. That's frustrating. And then here, negative 1 to the n minus 3 over n minus 2. It's a little weird that it's not, I was hoping it would cancel. And at 0 you just get a negative 1. Wait, what? I mean, I guess you don't get anything, right? Yeah, probably on the right there. Oops. Grr. We started at 1, of course. So yeah, never mind. Probably should have stopped early. You get this, and then this is actually squared probably, right? N minus 1, well, it doesn't have to be. So we'll write n minus 2 over n minus 1. What do you mean n minus 1? Well, I meant 1. You could do 1 if you want. Yeah, I was thinking alpha n minus 1 and b1. So let's do b1. It would look like this, and this is negative 2, but it's a square is the point. So this isn't there. So you're adding n at the end here. So like here you're, this time it's not symmetric, at least it doesn't appear to be, right? Here you've got an n in the denominator, here you've got 1 in the numerator. what was I supposed to be showing? It's, I was hoping to get coefficients like this partial, this is the coefficient. This is what I'm supposed to be proving, is that it equals, like, not, yeah, the nth coefficient would be the nth partial sum of a harmonic series is what I'm supposed to be showing. So, like, this is, like, is this equal to, you know, 1 plus half plus a third plus da 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 up to 1 over n. Oh, did I not negate the 2? This, no, I did it fine. He's got a negative 1 in one series, but not in the other. So I don't think I have a problem with that. But did I maybe miss a negative sign or something? No, you didn't. I'm using this result for when you take a product of two series. And I didn't miss a negative sign there either. So yeah, I don't know what happens to my negatives. You can see there, yeah, I don't quite get this one. I don't quite see it. You can see the harmonic part, obviously, right? But it's alternating harmonic business going to cancel somehow with these coefficients in particular? Because I got this. Let me see if he uses 43 to... Yeah, I did that and then used 34 and 38. Okay, fine. What was 38? So 34 was the thing I'm using. But 38, I don't... Oh, yeah, right. This equals this. That's hilarious. I just forgot that result. Okay, that's exactly what we have. Okay. This one was a weird one. This one comes from integrating. Yeah, of course. Sweet. So, alright, we got 43.1 down. You would need to know this. But this was kind of a funky one. It comes from, like, to get those in there, you start with a series like this, naturally, right? So if you had like 1 plus x to the n, you could express it like this. And then you're going to want to integrate to put a power in the denominator. So it's very similar to this 37, where you can differentiate to get a single power down. Here we're doing the opposite. But it also wasn't this function, it was something funky. But you can sort of, I slowly like cobbled it together earlier in the week or last week. So you can see, of course, if you did integrate this, you get, I mean, the powers aren't going to match up, right? So this is wrong. But we can fix it. We could divide by x, for instance. So if I had divided this by x, you'd get that. That's part of it. And then we also wanted the alternating bit. So you're going to need this to be a negative x. Is that all there is to it? I'm not sure. So this one would be this with an alternating, and like on the first term, yeah, so we want to multiply by -1 as well. You want to do something like that so that the first term is positive. So integrate this. Does that make some sense, I hope? And you'll get a series. Anyway, we don't need to do this again. I did this like last week, but oops, I forgot to divide. There's that. So then you get alternating jazz x to the k over k. And yeah, that's it. Now plug in 1. You still have to actually integrate this before you can plug in 1. But, you know, I'm just trying to recall how I would have done that. This is super basic, right? Yeah, I do need n up there. Yeah. And then why do you get, oh, I see. This is a u sub, huh? This is why it's tripping me up. That's not integrable right on its face. Anyway, whatever. This is negative dx, but when you, so if you transform this, you'll get u minus 1 downstairs, right? Eesh. Is it better? Yeah, evidently. Why is this better? Yeah, getting confused on some simple calc thing right now, but clearly it's been too long. Clearly it's time for a break. But yeah, you can just transform this and you'll get an answer. And then plug 1 into it. And you'll get this harmonic series. So yeah, if we use 38, we'll get an answer. I should trail off here instead of staring at this. Yeah, how is this not the transformation? It's gotta be this, right? So we end up with this, but yeah, sure. How do you want to handle that? Is it just, I mean, I don't remember it being anything special. parts. Huh, very strange. This should be easy. Did I get the function wrong? I don't believe so. Well, okay. So yeah, how do I... alright. I'm gonna cheat. See what he did back... Oh yeah, here it is. I did get the function wrong. Yeah, he has an extra 1 there. Oh, did I... Wait a minute, does his statement start with... Oh yeah, of course, it's gonna start with 1. It doesn't start with 0. Yeah, it starts with 1. I see. Duh. Okay. I kept starting with 0. Eep. Yeah. So if you were back here and you subtracted 1, and then you negate, you get 1 minus. You end up with this. Yep. So take this, minus 1, you get the series that we want where it starts at 1 instead. And the division scales it back, so it looks like this. And then you still have to integrate this, but should just be a u sub. So then we'd end up with 1 minus u to the n. Right, which I guess you could integrate term by term, I suppose. Is there a better way to do that? Nah, I'm not really seeing it. Did I miss a negative sign? Right, I did miss a negative sign. So this one's got a negative because of that negative dx. So we actually get the same as, we get this, basically. Well, I don't want to do it that way. we get this, which is 1, it's the integral of 1 plus u squared up to un minus 1. So integrate those, du, you'll get u plus half u squared, right? Plus a third u cubed, da. And then you can plug in 1 for x, or you could have integrated from 0 to x, 0 to 1. Would have also probably made sense. I guess you do need to integrate from 0 to 1. So over here, when you do that, you get your series, and at 0 you get 0, and at 1 you get what you're looking for. Yep, yeah, so you should probably do this integral from 0 to 1, and then it'll work out. Alright, ladies and gents, so that was 43.1. I just forgot about this identity. Alternating, yeah, that's confusing. I just didn't recognize it. it's also, it is kind of written, I wrote it backwards. So this is n choose 1. Yep, it starts with n choose 1, right? If I needed to recognize this is n choose 1, this is n choose n minus 2, it matches up with this, it's alternating. So yeah, that does fit the bill of looking like n1 minus n2 over 2 plus n3 over 3, etc. And it ends on 1 over n times n choose n. So yeah, I had these backwards. That's part of what tripped me up. But it's same thing. All right, folks. Thanks for tuning in. Have a fantastic day.